This talk is about S parameter definition in adapters with dielectrically loaded connectors, and I'd like to walk you. Oh, okay, sorry. So I'd like to walk you through this presentation. I'll start off with an introduction on what a dielectrically loaded connector looks like. Even maybe we have to move it a bit. Do it like this.
Feel like a rock star.
Okay, thank you. So, yeah, I walk you through this presentation. We start off with an introduction on what dielectrically loaded connectors are and why they are used. Then I'll present the method I use to characterize S parameters in there. And then we go to results and conclusion. So here is one of these. It's a Next 10 connector. You see it's a male connector. And on the opposite side you have a 3.5 millimeter female connector. And basically the question we got asked is, what are the S parameters of this? So this is not so easy to answer. In this figure, on top you see this connector you saw on the first slide. It's male to Next 10 female. And below there's a special kind of adapter. So you see it is special in this sense that it has only a very small part which is dielectric here. The rest is air dielectric. And this one is from Next 10 male to 3.5 male. So the 3.5 male interface is not such a problem to model, but the Next 10 interface is a problem because there's dielectric, and you see that this dielectric is staggered. Basically, there's a part going from the male side to the female side and crossing the reference plane. So here you see the Next 10 interface, and this connector exists in two varieties, so you can have them as a screw-on and as well as a snap-on connector. And if it comes in a snap-on variety, this is an additional problem because these snap-on connections, they're not very phase stable. So if we would try to do a conventional calibration with a calibration kit on this with a snap-on connector, that would not work very well because of the phase variability. So we need to go to use something different here. And this is the characterized adapter technique. So what we will do is basically we do unknown through calibration with female test port on both sides. We calibrate with short open load, and and then we connect this commercial adapter we saw on the first slide with the photo, and the special adapter, which has only very small dielectric. This B here stands for bead. And so we can do this measurement. And assuming that we know the S parameters from modeling of this one, we can determine the S parameters of that one. And once we know that one, we can make one additional measurement and know as well the opposite, the S parameters of the opposite adapter. And then we are done. So sounds easy, but first we need to know S parameters of this one. And as already said, there is this problem with these dielectric in the interface, because when you define S parameters, basically what you want is you want monomode propagation in the reference plane, and these dielectric interface definitely somehow makes it non-monomode or multimode, better to say. So what we use here is called extended S parameters, and to define them, first we define forward and reverse operation. This means we send energy forward through the interface and backward. And for these two cases, we define the power and current in the reference plane. So this is a power integral and a current integral. The current integral is a ring integral around the center conductor. From these two things we can derive the characteristic impedance and the extended S parameters in this reference plane. And then as a last step, we have to vary the very close by geometry, so close by to the reference plane, in order to see how this affects the S parameters of the device itself, but as well of the adjacent device. You will see this better explained in the following slides. Just to remind you, what's the difference between pseudo S parameters and extended S parameters? Pseudo S parameters are defined on modes, so you cannot define them in the reference plane I'm talking here about. And for pseudo S parameters, you don't have this fourth step, because you don't have to worry, because you're not allowed to change or vary geometry close to the reference plane. So here are the reference planes. Again, on the left-hand side, you have this commercial adapter you saw on the first slide with the photo. On the right-hand side, you have the special adapter, which you're going to characterize. And, oops. That was way too fast. So, I'm sorry for that. Yeah. So here you see a first trial to get confidence with these extended S parameters. So in full line you see the S11. So we go back to see what this is. So this is on this reference plane. With pseudo S parameters and with extended S parameters, and they completely overlap them each other. And here you see the difference between these two, between pseudo and extended. And you see that it's a very small difference. And it has to be said, this result was taken with COMSOL multiphysics, so there is as well some numerical error involved here. So next, and this is the fourth point I just spoke about, is varying close by geometry, and what is the effect of that. So what we are doing now is we vary this length L7, which is basically the recession of the dielectric from the reference plane, and this is a variation which is basically taking place in this special adapter, and in theory it should not affect the S parameters of the commercial adapter in simulation. So let's see how this works out. So this is a more busy graph. So you have S11 of the special adapter in the two cases with this L7 80 micrometer and 120 micrometer, and you see with these two lines there's a small difference. This difference, if you look at it carefully, this one, the dashed red line, is about 4 times 10 to the minus 3 in linear S parameters. And now we can look what is the difference, the maximum difference in the commercial adapter which we observe if we change this. Basically, if things go ideal, we would expect 0 difference here. But we cannot get this because of the special definition of our extended S parameters. And but you see the error we commit is very small. It is below 1 times 10 to the minus 3. And this is a special additional step you have to do when you do define extended S parameters, because you need to characterize this and take it into account as an uncertainty. So, sorry. Now we go on to the characterization plan. So now we know the theory, how to do it. Now let's see what kind of measurements and things we need. First we need to produce this characterizable special adapter from 3.5 millimeter male to next 10 male. We need an offset short and a reference bead. And then we measure the offset short. We measure the offset short when it is filled with this PTFE bead. And from these two measurements we can basically extract conductivity of the plating and the permittivity of the PTFE. Then we can model this special adapter, and then we can do the electrical measurements to transfer the S parameters from the special characterized adapter to commercial adapters. So let's see how that works. So here you see the empty offset short, the filled offset short, and from that we can basically derive the conductivity. So you see here the derived or extracted conductivity of the plating. I'd like to draw your attention to these values. This is basically copper beryllium gold plated. Most of you would expect much higher conductivities, but this is not the case due to there's a nickel layer for adhesion, which is making things worse, and as well surface roughness, and so you get this kind of behavior here. And additionally, I can say from the filled experiment we extracted the epsilon r of the PTFE, which was used here, as 2.02. The loss tangent was so small we could not get it with this technique. Sorry. Here's the results for S11 of the commercial adapter. What we did is we had 3 of these adapters which we characterized. So these 3 special adapters basically, and then we used each individually characterized special adapter to measure the S parameters of the commercial adapter. And this is what you see here. So these are the 3 adapters, and here are the 3 results. And basically this is the maximum difference you get. You see that there is already here in this, you see that there are modes above 20 gigahertz, but this is not an accident. We just measured further than the manufacturer of the connector intended us to do. And this is S21. We did the same for that, and here you even see the modes more clearly. Maybe it has to be added as well. So you see these higher order modes here. You didn't see them in the simulation, and this was because the simulation was done in a rotational symmetric setup. So in the simulation you cannot catch the first higher order mode in this. So it has to be said that the simulation is above 20 gigahertz is not really valid then. So, but up to here the results are good. This brings me to my conclusion. So we demonstrated how to use extended S parameters to characterize an adapter with dielectrically loaded connectors, and to how to establish traceability for that. We extracted conductivity of plating and dielectric constant, conductivity of plating and the dielectric constant, and which was not shown here, but we obviously have as well a full uncertainty budget for the S parameters of this, and with uncertainty budget and this technique, we establish basically traceability for the S parameters in this reference plane. Thank you.
So this paper is open for questions, please.
Go ahead. Come here.
I really missed the point, because probably I'm tired, but you talk about the role of extended S parameters. As far as I understand, that are the S parameter of some modes, right? Computed by the simulator, right?
The extended S parameters are S parameters in an arbitrary field. And this arbitrary field is defined by forward and reverse operation. So basically that's where they are specific to. They can be the same if you have, for example, a plain transmission line. This forward field can be the same as for a pseudo S parameter mode, and then they're the same.
Okay, I did not express myself. The extended S parameter is something related to modes, right? The question was not that. The question was, you measure traditional single mode S parameter because you calibrate the VNA with ordinary standard, right?
Yeah.
So I did not really catch how you put them together. To me, I understand the way you embed the part that you characterize. I understand that you determine the model by electromagnetic simulator. What I do not understand, why you need to define different S parameter and just not use the results of the simulator.
Okay. So basically the reference plane where I want to know the S parameters in the center of the connector, you can basically what you can do in simulation programs, you can put a S parameter measurement there, but it will be faulty because the simulator is assuming that you have only one mode propagating there, and which is basically not the truth.
Oh, I understand.
So you need to come up with a definition which allows for multi-mode or arbitrary field in the reference plane. And we are just using power and current to extract S parameters. From power and current we go to the transmission line equivalent model, and then we extract we get the S parameters. That's our technique. And the consequence of doing so is that basically you have to check what's happening if you're changing something very close to the reference plane, because then you change basically the field you're referring to, and this has as well consequences then to the adjacent S parameter block. And that's why I made this test when I changed L7. So, welcome.
We have time for one quick question, if any. Good, then let us thank Johannes one more time and introduce to your attention our third paper, which